So we're in chapter 4 this week. We're going to be learning about naming all kinds of different compounds, both ionic and covalent. And the first question that you might be asking is, why would an element want to form a compound? Well, it turns out that every element on the periodic table has a secret, yearning desire to have the same number of electrons as the nearest noble gas. So what they will do is lose or gain electrons so that they attain the same number of electrons as the nearest noble gas. So for instance, if you have your textbook handy, and if you don't, you might want to pause here and go grab it, and you open to the front cover and you're looking at your periodic table, and we find oxygen, for example. And in chapter 3, we learned about how to do the electron configuration of oxygen. Oxygen is element number 8, so its electron configuration is 1s2, 2s2, 2p4. Let's just write that out here. Oops. 1s2, 2s2, 2p4. Now the nearest noble gas to oxygen, there's two choices. It could go forward and become like neon, or it could go backwards and become like helium. Well, if we look at the number of electrons that helium has, it only has 2. Oxygen has 8. So that means that oxygen would have to lose 6 electrons to become like helium. It takes energy to lose electrons, and it takes energy to gain electrons, and atoms, when you get right down to it, are lazy. They only want to gain or lose the minimum amount. That will be the least amount of energy. So when we look from oxygen to neon, we see that it's only a difference of 2 electrons. Oxygen has 8, neon has 10. So oxygen will gain 2 electrons so that it can have the same number of electrons as neon. So what that ends up looking like is oxygen still has its 8 protons, but now it also has 10 electrons. So we know now, based on our what you learned in chapter 3, that this differing number of electrons and protons means that oxygen ends up with a -2 charge. Now, why an element might form an ion is this. Why it might form a compound is those electrons have to come from somewhere. So let's look, for example, then at lithium. Lithium is element number 3. Its nearest noble gas could be helium, which is behind it, or could be neon. Now, if lithium wanted to be like neon, it would have to gain 7 electrons. Lithium has 3 electrons, neon has 10 electrons, so that means lithium would have to add 7 electrons. Lithium only has 3 protons, so this is not very likely. On the other hand, helium only has 2 electrons. So if lithium wanted to be like the nearest noble gas, it would pick helium because it's a lot closer. In this case, lithium has 3 electrons. It wants to be like helium, which has 2, so lithium will lose 1 electron. So lithium will end up with 2 electrons and 3 protons, which we know leads us to a charge of +1. Now, what's really handy here is if you look at all of the alkali metals. So lithium is an alkali metal. It's in the column of alkali metals. I think we probably learned this in chapter 1. All of the alkali metals are all 1 away from their nearest noble gas. So all of them, when they form ions, will form the same charge. All of them will be a +1. If we head over 1 column to the second column, starting with beryllium and ending with radium, those are the alkaline earth metals, and they're all 2 electrons away from the nearest noble gas. So they all will form a +2 ion. If we go all the way to the halogens, which is group 7A, or group 17, depending on your labeling there, we find fluorine, chlorine, bromine, iodine, and astatine, and all of them, if you think about it, are 1 away from a noble gas, and all of them will gain 1 electron to attain those noble gas status, which means that the halogens, when they form ions, are all -1 ions. So go ahead and figure out for oxygen's column and nitrogen's column what general ions you would come up with. So for oxygen, like we said, was only 2 away, and everybody else in its column up to tellurium, right? Because between tellurium and polonium, what happens is we cross that non-metal to metal boundary, and it turns out that non-metals gain electrons and metals lose electrons. So what we're going to say in terms of charge is only applicable from O to Te, which is that they would be -2s. Nitrogen to arsenic would all be -3s. So what ions would each of the following form? We're looking at calcium. We find calcium on the periodic table. It's element 20. Its nearest noble gas is argon, which has 18 electrons. So calcium will lose 2 electrons to have the same number of electrons as argon, in which case then calcium will form a +2 charge. Bromine is one of our halogens. It's 1 away from a noble gas. Bromine has 35 electrons. Krypton, its nearest noble gas, has 36, so it will form a -1 charge. Phosphorus is element 15. Its nearest noble gas is argon with 18 electrons. Phosphorus, therefore, will gain those 3 electrons so that it can have a similar number of electrons as argon, and so phosphorus will be a -3 charge. Notice when we're gaining electrons, we're ending up with more electrons than protons, which means we end up with negative charges. When we're losing electrons, we end up with more protons than electrons, which means we end up with positive charges. Oh, and there's a periodic table for you to look at to do all this on. Okay, what is an ionic compound? It's going to be a metal paired with a nonmetal. And we just talked about the fact that metals generally lose electrons, which means that they will form positive ions, which are cations, and nonmetals will gain electrons, which will form negative ions, which are anions. So an ionic compound is also a cation plus an anion, in that order. The overall sum of the charges on your ions has to equal 0. And the formula that you write for the compound will contain the lowest whole number ratios of metals to nonmetals. So let's do some examples. You might be asked, what is the formula of the compound formed between calcium and bromine? So the first thing we want to check is, are we talking about an ionic compound? Do we have a metal and a nonmetal? So we go to our periodic table. I think I have one. Oh yeah, right here. And we see that metals are to the right of the dark jagged line that runs down here, and that nonmetals are to the left over here. So calcium is indeed a metal, and bromine over here is indeed a nonmetal. So we do have a metal and a nonmetal paired together. So since this is an ionic compound, we know that calcium and bromine are going to form ions, and then they're going to pair up. So what we need to ask is, what ion will calcium form? Well, calcium has 20 electrons in its neutral atom state. Its nearest noble gas is back here at argon with 18. So calcium will form a +2 charge. Bromine, we just worked out. Actually, we did calcium too. Bromine is right next to krypton, its nearest noble gas. Krypton has 1 more electron than bromine does, 36 electrons versus 35 electrons. So bromine will gain 1 electron. So let's go back and write this down. So calcium, like I said, will form a +2 charge. And bromine will form a -1 charge. So now that we've figured out the ions that will actually form, we need to come up with the actual compound formula. And if you'll recall from back here, we said that the overall sum of the charges has to equal 0. So that means when I'm here with my calcium and my bromine, I need to make sure that I have enough calciums and enough bromines to add to 0. Well, right now, calcium has a +2 charge, and bromine has a -1. So if we write this as though we're doing addition, right now, my total charge would be +1. Well, that's not going to work. I need a total charge of 0. I can only add more bromines or add more calciums. I cannot add other elements. I cannot change the charges on the calcium and the bromine. So if I want this to add to 0, it makes sense that I would add another bromine because it brings another -1. So now we get a +2 from the calcium and a -2 from the 2 bromines, and that totals 0. So how do I take this information and make a formula? Well, remember, formulas are the elements written with numerical subscripts telling us how many of each there are. So calcium, there's only one of, so I just write calcium. And bromine, there is two of, so I have Br2. So the formula of the compound formed between calcium and bromine is CaBr2. So let's go ahead and do this for sodium and nitrogen. So let's go look at our periodic table. Maybe I'll look at my periodic table. And we see that sodium is right here. It's one of the alkali metals in the first column. We know that all of them have a +1 charge. And if you don't want to memorize it that way, you can work it through every time. Sodium has 11 electrons. Its nearest noble gas is back here with neon, which has 10 electrons. That's one less electron than sodium, so sodium will lose an electron, making it a +1. Nitrogen has 7 electrons in its neutral atom form. Its nearest noble gas is also neon, which has 10. And notice it's 1, 2, 3 electrons away. So that means that nitrogen will have a -3 charge. So sodium we decided is a +1. Nitrogen we decided is a -3. So right now, if I just added those two together, if I just had one of each, I come up with a -2 charge. But I need a total charge of 0. I can add more sodiums. I can add more nitrogens. And if you think about it, it makes more sense to add the positive thing here because we want to cancel out that -2. So if I add 2 more sodiums, then I end up with a +3. Let's see if I can write there. +3 from my sodiums and a -3 from my nitrogen, which gives me a total of 0 for my charge. So now I've got 3 sodiums and 1 nitrogen. I'm writing my metal first, always. There's my sodium, and I have 3 of them, so I have a subscripted 3, and then I have nitrogen. Now let's say you had decided that actually I need 6 sodiums and 2 nitrogens. Maybe that's what you came up with. That works in the sense that the total charge equals 0, but it violates one of the other rules that we had, which was the formula has to contain the lowest whole number ratios of metal to nonmetal. So if you think about it, Na2, excuse me, that wasn't what we were doing. Na6 and 2 does not have the lowest whole number ratios because I can divide 6 by 2 and I can divide 2 by 2. So my lowest whole number ratio is Na3N, which is my correct answer. Which is what we had here. There's our periodic table again. So, your turn. Go ahead and give the formulas for the compounds formed from the elements below. You'll want to hit pause here and actually engage in this activity. And then go ahead and hit play again when you're ready. So, potassium and sulfur. Potassium will form a +1 charge. Sulfur will form a -2 charge. I need to have enough potassiums and enough sulfurs so that the whole thing adds to 0. So I will need 2 potassiums, because that way I will have a +2 coming from the potassiums and a -2 coming from the sulfurs. Since I have 2 potassiums, it gets written K subscripted 2S as my answer. Let's say you wrote K2S. Is that okay? No, that's not going to work. You need to make sure you subscript. You also need to make sure that you're writing the element symbols correctly. Potassium is always written as an uppercase K, and sulfur is always written as an uppercase S. Strontium and phosphorus. Strontium is a +2 charge. Phosphorus is a -3 charge. So this is a little bit more complicated. I can't just add more of one of them. I need to think about what the lowest common multiple of 2 and 3 is, which if you think about it, you'd come up with 6. So that means I need to have enough strontiums to equal plus 6 and enough phosphorus to equal minus 6. So if you think about it, that means we need 3 strontiums and 2 phosphorus. This gives me plus 6. This gives me negative 6. Whole thing adds to 0. So my formula is 3 strontiums, right, my metal first, my nonmetal second, and 2 phosphorus. Lithium and iodine, our last one here. Lithium forms a +1 charge. Iodine forms a -1 charge. And oh look, I have enough of each to equal 0. So in this case, I just need 1 lithium and 1 iodine. Box my strontium too. Sometimes we want to actually be able to name these things. So we're going to sort naming according to a couple of different characteristics. And the first one we're going to do is whether or not the metal has a fixed charge. So your fixed charge metals, if you go back to your periodic table here, your fixed charge metals are going to be all of your alkali metals, all of your alkaline earth metals, and then silver. And aluminum, actually. Those are your fixed charge metals. And what fixed charge means is that whenever I have any of these, I always know what their charge is. So alkali metals, we said they are always +1. And alkaline earth metals, which are the second column, we said were always +2. Turns out silver is always a +1, and aluminum, which for some reason is missing its L there, is always +3. Let's go, whoops, back here. So when we're naming these, we're checking to see, am I dealing with a fixed charge metal? If I am, then I just name the metal and then the anion. So for instance, I might be faced with this formula here, Mg3N2. Now notice the names of the anions are slightly different than the names of the elements for the nonmetals. So nitrogen has become nitride. Oxygen has become oxide. Sulfur has become sulfide. Phosphorus, phosphide. Carbon, carbide. Selenide comes from selenium. Fluoride comes from fluorine. Bromide comes from bromine. Iodide comes from iodine. And chloride comes from chlorine. So when I'm looking at this formula, I need to name the metal first. And the metal is magnesium. So magnesium, spelled correctly. Spelling does count when it comes to naming. And then I need to name the name of the anion. This is nitrogen, but it's present in an ionic compound because it's paired with a metal. So that tells me that nitrogen is actually present as an anion. So I need to name it as such. So this is magnesium nitride. And that's the name. Now notice the name doesn't say anything about the fact that there's 3 magnesium and 2 nitrogen. And the reason for that is because it's implied. Magnesium is always Mg+2. Nitrogen is always N-3. So based on the rules that we talked about in determining formulas for ionic compounds, because we know that they always have to add to 0, I would always, given magnesium nitride as a name, come up with this as the formula. So my name doesn't actually need any more information. So go ahead and name the following compounds. Take a moment, hit pause, name those, and then we'll come back and go through them together. Okay, so first thing I want to check is, do I have an ionic compound? Yes, I have a metal and a nonmetal. The second thing I want to check is that a fixed charge metal? Well, calcium is an alkaline earth metal, which we know is one of the fixed charge metals. It's in the second column. So I just need to name the name of the metal and the name of the anion. And I'm looking at calcium and oxygen together, and we know that the name of oxygen when it becomes an anion is oxide. So this is simply calcium oxide. Down here, I've got sodium and I've got sulfur. It's a metal and a nonmetal. It's a fixed charge metal. Sodium is one of the alkali metals, so I'm simply going to name sodium. And then I'm going to name sulfur as an anion, which is sulfide. I've got potassium and bromine paired up down here. Potassium is a metal. It's a fixed charge metal, so I'm just going to name potassium and bromide. Sometimes in your ionic compounds, you'll run into compounds that contain polyatomic ions. And if you've been looking at your blue sheet and you have it readily available, if you don't, you might want to hit pause and go grab it. It lists all the polyatomic ions that you have to have memorized. And it shows both the name, the formula, and the charge. And you need to know all of that information because you'll be applying it in naming ionic compounds and in coming up with formulas of ionic compounds. So when you're looking at an ionic compound that contains a polyatomic ion, you'll recognize that it contains a polyatomic ion because you'll have memorized them. But the formula idea works the same. You're still going to need enough positive ions and enough negative ions to equal 0. The positive ion will always be written first, and the negative ion will always be written second. With polyatomic ions, we will find that we use parentheses if we need more than one polyatomic ion to show that we need the whole thing rather than just parts of it. When we're naming, you're just going to name the polyatomic ion with its name, nothing special. So for example, what is the formula of magnesium nitrate? Well, what we need to be aware of is what's the charge on magnesium. Whoops, it just erased my M. Oh, it's back. What's the charge on magnesium? And you can go back and check your periodic table and determine that the charge on magnesium is +2. It's in the alkaline earth metals. It's 2 away from the nearest noble gas, so it will lose 2 electrons. And then nitrate, if you haven't memorized your polyatomic ions yet, it's good to have that blue sheet close by. It has a formula of NO3 - 1. So same application, or same type of process that we had when we were dealing with just nonmetal anions. I have a +2 on my magnesium and a -1 on my nitrate. I'm going to need 2 nitrates so that my total charge equals 0. So how do I write this in a formula? Well, I still write the magnesium first, but I have 2 nitrates. So what I'm going to do is put the nitrate into parentheses and subscript a 2 on the outside. That tells me I have 2 nitrates. If instead I had written something like Mg2NO3, that's not going to work. Or Mgn2O6, that also doesn't work. You want to look for this setup for magnesium nitrate. So then our second example down here says, what is the name of Ca3PO42? Well, do we have a fixed charge metal? Yes, we do. Calcium is an alkaline earth metal, has a fixed charge. So that means we're just going to name the name of the metal and then the name of our anion, which in this case is a polyatomic ion. And up here we said that when we name, we just name the polyatomic ion. So PO4 with a -3 charge is the phosphate ion. So therefore the name of this is just calcium phosphate. And again, spelling counts, so make sure you spell correctly. Sometimes you'll have ionic compounds that have transition metals. So these are all the other metals that we were looking at on the periodic table that weren't fixed charge metals. So remember, fixed charge metals were column number 1, column number 2, silver, and aluminum. So everybody else who's a metal is considered to be a variable charge metal. And what that means is that they can have different charges. And so that means that when we go to name them, we need to have some other information that goes in the name. And we also need to figure out what their charges are. So for example, you might be looking at FeO, Fe2O, and Fe2O3. All of these are iron paired with oxygen compounds. But when we find iron on the periodic table, we find that it's not in the first two columns, and it's clearly not silver or aluminum, so it is not a fixed charge metal. So the question is, how do we calculate the charge? Well, let's do FeO as an example. We know that the total charge of our positives and our negatives has to add to 0. And we also know that the charge on the oxygen is fixed. All the nonmetals have fixed charges. So oxygen, we can look on the periodic table and determine, oh yeah, oxygen has a -2 charge. Iron, we have one of, we don't know what its charge is. But we know that whatever it is, it has to equal 0. It has to add to 0, excuse me. So if you think about it, if oxygen is -2, and I've got one iron, and the whole thing has to add to 0, then iron must have a +2 charge, which it does. Let's look at the next one, Fe2O. Again, oxygen has a -2 charge. The whole thing equals 0. We don't know the charge on each iron, so I'm going to represent that as 2x. The 2 is coming from the fact that I have 2 irons. The x is the charge, which I don't know. So then we can solve it like an algebraic equation and discover that x equals +1. So the charge on the iron, therefore, is +1. Fe2O3, go ahead and hit pause for a moment and calculate the charge on the iron. Okay, so in Fe2O3, we've got a -2 from the oxygens, but there's 3 of them. This is going to total 0, and I've got 2 positive charges on the iron that I don't know what they are. So this ends up being 2x minus 6 equals 0. 2x equals 6, so x equals +3. So the charge on the iron is a +3. So what is the charge on each of the following metals? Go ahead and hit pause and run through this. Okay, on this first one, we see that the sulfate polyatomic ion is part of the compound. And sulfate, if you've memorized this, if you haven't, you should get started on that memorization, has a -2 charge. There's 1 copper plus that sulfate, which tells me the whole thing has to equal 0, so copper must have a +2 charge. So Cu +2. AuCN, cyanide, again, another polyatomic ion, has a -1 charge. 1 cyanide, 1 gold means that the gold must have a +1 charge to make the whole thing equal 0. Cobalt paired with phosphide. Phosphorus we know, we don't know cobalt, but phosphorus we do know from the periodic table is a -3. And again, 1 of each, so cobalt must be a +3 charge. When we go to name these compounds that include variable charge metals, like I said when we started talking about this, we need some additional information in the name that will tell us what the compounds, what the charge on the metal is. So we just went through and calculated the charge on each of these metals. Now we're going to name them. The name is going to include a Roman numeral in parentheses that has the charge. So now when I go to name these compounds, it'll be the name of the metal, then in parentheses, the charge on the metal, and then the name of the anion. So it's very similar to what we were doing with fixed charge metals, except we need this Roman numeral that tells us the charge. So copper, we decided in the previous slide, had a +2 charge. So that means the name of this is copper. Copper. Oh, shoot. Let's erase. I'm making a mess. My smartboard is not keeping up with me. Copper. Get my mouse out of the way. Roman numeral in parentheses 2, because copper has a +2 charge, and then the name of the anion, which is sulfate. gold, we decided had a +1 charge. So this is gold, Roman numeral 1 in parentheses, cyanide. Cobalt had a +3 charge. So cobalt, Roman numeral 3. And we're going to name our anion, which is phosphide. So go ahead and take a moment and give the name or the formula of each of the following. Go ahead and hit pause. Okay, so nickel, Roman numeral 2 carbonate, tells us that the nickel has a +2 charge. Carbonate is one of your polyatomic ions, and it has a -2 charge. So in order to make the whole thing equal 0, I just need one of each. So I have nickel, and 1 carbonate. In the next one, the SRO, I need to ask myself, am I dealing with a fixed charge metal or a variable charge metal? So go ahead and find strontium on your periodic table. It's element number 38. Is that a fixed charge or a variable charge metal? Well, it's fixed charge. It's in the alkaline earth metal column, and we know that all of those have a +2 charge. So because it is a fixed charge metal, we go back to our first way of naming, which was just to name the metal, no Roman numeral because this is fixed charge, and the nonmetal, anion. So strontium oxide is the name of SRO. When we look at PTS2, we see that platinum is not a fixed charge metal. It's element 78. It's not in the first two columns. It's not silver. It's not aluminum. It's not fixed charge, which means it's a variable charge metal, which means that we need to include a Roman numeral that tells us the charge on the metal, which means I've got to figure out what that charge is. So when we look at this, we see that the sulfur, there are two sulfurs, each of which has a -2 charge. We don't know the charge on the platinum, but we do know the whole thing has to add to 0. So this is x minus 4 equals 0. So x, the charge on the platinum, equals +4. So now I know the charge on the platinum, I can write the name. It's the name of the metal, platinum, Roman numeral 4, and then the name of the anion, which in this case is sulfide. There you go. Hopefully you got those all right. Covalent compounds. This is the last of our naming types of compounds that we're going to do in Chemistry 121. These contain 2 nonmetals, and what that means is that there are no ions. So you're not losing or gaining electrons here. It turns out that in a covalent compound, the bond that's formed is actually formed by the 2 atoms sharing 2 electrons. So no ions, no positives or negatives. When you make a covalent bond, like you can see here with hydrogen, each hydrogen brings a single electron as represented by a dot. There's hydrogen's 1 dot electron. They get together and share those 2 electrons, which makes a covalent bond. So this is an alternate way of elements being able to attain noble gas status, or access to 8 electrons. In hydrogen's case, it only wants 2, by sharing rather than totally giving up or gaining electrons. When we name covalent compounds, that means we need some information in the name that tells us specifically how much of each element there is. We're still going to name them as though they're a cation and an anion. So we'll name the first element first, just using its name, and we'll name the second element as though it's an anion. And you actually already have some real-life experience with this. Take a moment and think about what is the name of CO and what is the name of CO2? Got those in your head? Well, you probably came up with the fact that CO is called carbon monoxide. And that CO2 is called carbon dioxide. So notice that we included numerical prefixes. The mono here telling me I had 1 oxygen, and the di here telling me I had 2 oxygens, to show how many of each type of atom, except there's no mono on the first element. So even though I had 1 carbon here and 1 carbon here, there's no mono written for the first element. And that's just convention. It's the way it is. Numerical prefixes, in case you don't remember them, mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7. That's one that sometimes surprises people. Octa is 8, nona is 9, and deca is 10. So it's a good point at this point to kind of stop and ask, now that we're going to be faced with all these different types of compounds, variable charge metal compound, ionic compounds, fixed charge ionic compounds, and covalent compounds, what kind of questions should you be asking yourself as you're faced with a list of compounds that you need to name? Well, the first question that you want to ask is actually shown here at the top, which is, does the compound contain a metal and or a polyatomic ion? If it does, then that means it's definitely an ionic compound. If a polyatomic ion is present in that compound, then you're just going to name the polyatomic ion. If there isn't a polyatomic ion present, then it's a binary ionic compound, which just means that it only has 2 elements rather than more than that. We'll do the full name with the Roman numeral if it's a variable charge metal, and we won't do the Roman numeral if there isn't a charge metal. If the compound doesn't contain an ion, then that means it's not an ionic compound, and that means, let's just augment our flowchart here. That means you have a covalent compound, which means that you're going to include prefixes for how many there are. I'm going to run out of space there. So let's practice. Go ahead and take a moment. Well, actually, it should take you a couple of moments. Hit pause and name each of these compounds. And each time you're faced with coming up with a name, ask yourself, does it have a metal? If it does have a metal, is that metal a fixed charge metal or a variable charge metal? Okay, go ahead and hit pause. All right, so PCl3, when we look at it, we see that the P phosphorus is a nonmetal and chlorine is a nonmetal. So that means that this is a covalent compound, which means that I need to name it using numerical prefixes telling me how many of each type of element there are, except no mono on the first one if it's only 1. And that's what we see. Phosphorus, there's only 1 atom. So we're going to name this as phosphorus, spelling correctly. And there's a 3 down there on the chlorine, so that means I have trichloride. NO, our next one, also covalent. No metals there. So also only 1 element on the first type of atom, so nitrogen. 1 element on the second type of atom gets a mono. And you can either say monooxide or monoxide. It does not matter. I'm going to say monooxide here. In my third example here, I have NaCN. Na is a metal. So then we ask ourselves, is it a fixed charge metal or is it a variable charge metal? And sodium is located in the first column of the periodic table. It's an alkali metal, so it's a fixed charge. It has a +1 charge all the time. So that means I just name it as it is. There's no Roman numeral, no numerical prefixes. it's just sodium, and then the name of the anion that it's with, which is a polyatomic ion, sodium cyanide. And the next one, I have Fe, which is a metal, and it's not a fixed charge metal. So that means that I'm going to need to calculate the charge on the iron. So I'm going to go over here and look at my hydroxide and see that each hydroxide is a -1, and that there's 2 of those. So I have 2 times -1 from the hydroxides. I have 1 iron that I don't know the charge of. The whole thing has to equal 0. So X, the charge on the iron, must be +2. So that means the name of this compound will be iron, Roman numeral in parentheses of the charge on the metal, 2, and then the name of the anion, which is hydroxide. In my last example, I have SO3, no metals. This is a covalent compound. And let's just for kicks make this S2O3, because I see that I've only got examples of 1 atom on the first element, and I want to make sure you understand that if there's more than 1, we name it differently. So because now there's 2 atoms of sulfur, if you named it just as SO3, you would have come up with sulfur trioxide, and that would be completely correct. If there are 2 sulfurs, then it is disulfur trioxide. Okay, homework problems for practice. These are all going to help you practice either determining what the ion charge is, determining the compound formula, or determining the name of the formula of all the different types of things that we've learned about in this section. Naming crosses both Chapter 4 and a little bit at the very end of Chapter 5, and because I like to keep all the naming together, that's why these are in sort of different places. So I've listed out the relevant problems that you would find good help for learning how to do this. And I encourage you to do, in Chapter 5, I encourage you to do all of those because there's not very many of them. And then in Chapter 4, do at least the odds I would encourage you to do. Okay? All right.